Hey, the topic we're looking at today is Riemann sums. This corresponds to section 5.3 in the textbook. So, Riemann sums are kind of the formal way to talk about approximating area under the curve. So we looked at last section initially with the right and left hand rectangles. Drawing those, getting more and more of them, gives you a better approximation. Riemann sums is kind of the formal way to talk about area under curve approximations using rectangles. So if we look initially, our first example here, so partitions of unequal width. So it's very important to look at your x row there. 2 to 3, 3 to 5, 5 to 8, 8 to 10. So unequal width. You have to keep that in mind when you're calculating the approximation. So the one from 2 to 10, and using an upper sum rectangle approach. Now the upper sum rectangle approach, what this means is you're using Riemann sums. And when you're doing Riemann sums, that's kind of your red flag you want to think about. Riemann sums mean to draw a picture. So if you're not already given one, you want to quickly create one. It doesn't have to be perfect, but just make something you can look at, you can help you visualize. You're drawing a picture, and then you're going to use geometry. So Riemann sum again to find an approximation, no calculus required. So let's draw a picture for this data. So x and y axis will go 2, 4, 6, 8 up to 10. Now we're not doing 5 rectangles with intervals of 2, we're letting n equal 4. That means 4 rectangles. Boy, that E is really depressing me. Let's zoom in. I want to get this right. Better. So 4 rectangles. So when you go to draw the rectangles, let's get our data points first. So 2, 5, let's go 2, 4, 6, 8, 10, 12. So let's label those. And it's not always necessary you do an equal interval. Sometimes I'll just draw y tick marks where my values are, just to expedite the process. Expedite the process. So first 2, 5, graph that. So 2, 5, about right there. We have 3, 7, about right there. 5, all odd numbers. 5, 11, right here. 8, 10. Oh, even numbers, good deal. And 10, 6, okay. So the curve looks something like this. Now, something like that. That's not exact. It doesn't have to be, because we're going to use the rectangles to make an approximation. We're doing an upper sum approach. So what that means is you have to switch between the right bound and the left bound as each one is appropriate, as each one gives you an upper sum approach. So a lower bound approach would be like, what's the least possible area? Upper sum, what's the most possible area? So every rectangle we do is going to be an overestimate. So depending on the curve, when it's increasing, you're going to use right bound. When it's decreasing, you're going to use left bound. So from 2 to 3, that's the first rectangle we're going to do. So there's our first rectangle. Then from 3 to 5, do this one next. And down. And then from 5 to 8, we're going to switch, because 5 to 8, we're start decreasing, so we're going to do a left bound. That gives us the rectangle going over the curve, giving us a higher area than we think. And then 8 to 10, again, doing a left bound. So the rectangle is over the curve. And what you have drawing, it's really simple arithmetic. So the first rectangle is height of 7 with the 1. So 1 times 7. Your second rectangle is a width of, let's see, 3 to 5, so 2 by 11. The third rectangle from 5 to 8 is 3 height of 11. So 3 by 11. And the final rectangle, 8 to 2, 8 to say 10, so with the 2 height of, with that height, 10. So 2 by 10. So 1 by 7, 7, 2 by 11, 22, 3 by 11, 33, 2 by 10, 20. Add all those up. And you get an upper sum approximation of 82. Okay, so no calculus required. Midpoint sums in the midpoint rule. So you've seen a midpoint before, halfway from one point to another. So this formula is really a really fancy way of saying the summation. I don't do that in there, so summation of all the rectangles, of those rectangles are height and base. So all the rectangles, base times height, then add them all up with the summation, however many rectangles you have. X sub 1, x sub I, and x sub I plus 1 are consecutive endpoints of the ith rectangle. So you're using consecutive endpoints. So use the midpoint rule to approximate. Again, those kind of keywords, those together should tell you, bring this down, that you're using geometry. So draw a picture if you don't have one, add them all up, all the rectangles. And what else do they say? There's our function, f(x), above the x-axis, and there's 2 to 6. 4 rectangles of equal width, so equal width rectangles. So have a graph here. Now we want midpoint rectangles, so halfway between the intervals. So you have a little underestimate, you have a little overestimate. And that's supposed to give you a pretty good approximation. Kinda the theory is better than only right or only left. Each rectangle you get a little both. And the theory is they kind of can average out better. Now it's still only approximation. It's not exact, okay? So our intervals, we have delta x is 1. because we're going from 2 to 6. Alright, so 2 to 6, 4 total, 4 equal rectangles, delta x is 1. So delta x is our base. Now, for each of these rectangles, we gotta find the height. And the height is going to be how far up from the x-axis the point is on the curve. Well, we have an equation for the curve. 8 over x squared plus 1. So we need our midpoints. From 2 to 3, those are consecutive x values. So 2 plus 3 over 2, it is 5 halves. So to find the height of the rectangle, you'll plug 5 halves into this equation up here. And then 8 over 5 halves squared plus 1, that'll give you the height of the rectangle times your base. Base times height. So can they come over here? Nope, don't write in highlighter, that's won't be clear. So area is our height, 8 over 5 halves squared plus 1, times our base. Well, our base is 1, so why write it, okay? And we want every rectangle. So you have 3 to 4. So you have 3 plus 4 over 2, which is 7 halves. So I have 8 over 7 halves plus 1. There's our second rectangle. Now we need the third from 4 to 5. So 4 plus 5 over 2, more commonly known as 9 halves. So our third rectangle, 8 over 9 halves squared plus 1. And now our fourth rectangle from 5 to 6. So we'll use both of those. 5 plus 6 over 2, which is 11 halves, so 8 over 11 halves squared plus 1, and we have our approximation for area. Now here's the nice thing with the FRQs. You can leave that as your numeric answer. The multiple choice, if they have it simplified down, you'd have to simplify all of it down, which, by my experience, they won't be this complicated with squaring of fractions and adding all of that together. They would be simpler numerically if it was multiple choice and you had to simplify it down. Because their main focus is not can you do arithmetic. Their main focus is can you do the underlying processes. Do you know how to start each problem and get the right answer? Getting the right answer is not their main concern. There's a trapezoidal rule also. I don't use this formula often, because it's kind of limiting. It requires equal partitions. So the width of every trapezoid must be the same. Now, I've seen this formula be like, hey, which of these would give you the area of this approximate area under the curve? And they'll have this formula filled out, so you kind of have to identify it. but as far as using it, I don't use it much. It's there for you to use. You can. I suggest you practice it. If you have equal partitions, so pi over 4 partitions, just remember that it starts at 0, so that's your x sub 0 term. Pi over 4 would be your x sub 1, the end of the first interval. So from x sub 0 over to x sub 1. That's the first interval, the ith rectangle, ith 1. From pi over 4 to pi over 2, so pi over 2, that would be your x sub 2, the end of your second interval. The third barrier, the third x value, but the third x value is the end of your second, hand doesn't work. Why am I doing that? Your second rectangle. 3 pi over 4, that is x sub 3. And pi is x sub 4. So take a look at example 3 and then example 4. Example 4, I strongly suggest you draw a picture. And then check your answers with my completed note online.